We're now ready to take a look at an example of working with the exponential distribution. So let's let x equal the amount of time, which is measured in minutes, that a postal clerk spends with his or her customer. So already we're probably thinking in terms of how long a postal clerk spends with his or her customer. Probably most of those interactions are going to be very short, and very few of them will be long. Maybe you go to the post office and you find out that your package didn't arrive and you need to kind of track down where it is. Maybe the postal clerk spends a little bit more time with you. The time is known to have an exponential distribution with the average amount of time equal to 4 minutes. Okay, so in this case we're saying x is a continuous random variable since time is measured, right? Time is continuous. There is always time between any two times that you state. So between 0 minutes and 1 second, you have half a second. It is given that mu is equal to 4. So we can write that x is exponentially distributed, and now the average is equal to 4. The average time is equal to 4. So mu is equal to 4, but we know that mu is equal to 1 over lambda. We're going to need lambda because that's the actual value that goes in for our decay parameter. So to find lambda in terms of mu, I can multiply both sides by lambda and then divide by mu. So lambda is equal to 1 over mu, which is equal to 1/4 or 0.25. Okay, so that means our lambda is equal to 0.25. That's ultimately what we need to be working with when we're calculating probabilities. And so what we're going to see is something that decays rather rapidly. This is a 25% per minute decay rate. So we're going to see something that really quickly decays, and in fact we'll see that when we compute probabilities. And so we can see here that mu is equal to 4 minutes. That's the average amount of time. So I don't know precisely where that will be, but our average is let's say there. Mu is equal to 4 minutes. And this is the time in minutes, and this is our density function. Find the probability that a clerk spends 4 to 5 minutes with a randomly selected customer. So we want to know what's the area under the curve between here and say there. That's going to be 5 minutes. So we want to find the area from time 4 to time 5, x equals 4 to x equals 5, of our density function, and we know that this is going to be lambda e to the negative lambda x, so 0.25 e to the negative 0.25 x dx. Now we know that the integral of this function, by the way, the integral of lambda e to the negative lambda x dx will always be negative e to the negative lambda x. So that saves us a little bit of work there. So this is going to be negative e to the negative 0.25 x. And now all we need to do is evaluate this over the interval. So we'll have negative e to the negative 0.25 times 5 minus negative, which would be plus, e to the negative 0.25 times 4. So we have negative e to the, which will be negative 1.25, plus e to the negative 1. And that comes out to approximately 0.081, which is 8.1%. So there's about an 8% chance that the clerk spends 4 to 5 minutes with a randomly selected customer. So not a high likelihood. That's kind of a long time, but about 1 in every 10 roughly, about 8 in every 100 customers will be there for 4 to 5 minutes. Half of all customers are finished within how long? Okay, so what we're really asking for is the 50th percentile. So we're looking for what value of x, right here is such that the area to the left will be 50%. So we're going to find the integral from 0 to x of our function, and we want that to equal 50%, or 0.5. Now we know that that integral, based upon what we've established up here, is going to be e to the negative 0.25 x. To evaluate that from sorry, it should be probably t, should not double dip on those variables. And we want that to equal, like I said, 0.5. So this will give us negative e to the negative 0.25 t, and then minus negative, which would be plus e to the negative 0.25 times 0, and we want that to equal a half. So e to the 0 is going to be 1. If I subtract that over, I'll get negative e to the negative 0.25 t equals negative a half. And so I can cancel out the negatives. And now I can take the natural log of both sides and use properties of logarithms to actually see that the natural log of e, that we can bring this power in the front, and natural log of e is equal to 1, so we'll get negative 0.25t equals the natural log of 0.5. And then finally we can just say t is the natural log of 0.5 divided by negative 0.25. So the natural log of 0.5 divided by negative 0.25 gives us about 2.77 minutes. So that means that 50%, half of all customers, will be done in under 2.77 minutes. We know that on average, right, average is different. That's if you were to, and we have to keep in mind here that this distribution goes on forever. Our mean is somewhere over here. Mu is equal to 4. So we see that the mean is larger than the median. The mean is larger than the median. Okay, and that's probably going to be because there are very few customers who spend a lot of time, but there is going to be somebody out here who's maybe there for 20 minutes. And so what that's going to do is it's going to pull the mean out towards 20 minutes, but the median does not get affected by outliers. So the median might actually be a better measure of center here, just because that mean is being pulled by those extreme outliers. But still, 50% of customers are there for fewer than 2.77 minutes, and the mean is probably higher just because you have, even though very few, you have those 1 or 2 people who spend a lot of time there. Let's take a look at one more example. On average, a certain computer part lasts 10 years. The length of time the computer part lasts is exponentially distributed. Okay, so the length of time the computer part lasts, we'll define that to be x. It is exponentially distributed. We know that the mean is 10 years. We're going to need to get lambda. Lambda, mu is equal to 1 over lambda. And so that means that lambda is equal to 1 over mu, which is 1/10, which is 0.1. So x is exponentially distributed with lambda 0.1. Okay, well that means that our density function is 0.1 e to the negative 0.1x. And in this case, we want to know what is the probability that a computer part lasts more than 7 years. So we'll just kind of sketch our exponential distribution. And we'll say here is 7 years, and we want to know the area beyond that. So how are we going to do this? Well, there's a couple of different ways. We could integrate out to infinity. So we can say that we want to know the area from 7 to infinity of 0.1 e to the negative 0.1x dx. We know that the antiderivative is going to be negative e to the negative 0.1x from x equals 7 to x equals infinity, not 8, but infinity. And so that will be negative e to the negative 0.1 times a very, very large value minus negative or plus e to the negative 0.1 times 7. So this is going to be 0 because you're taking e to a very large negative number. And then we'll have e to the negative 0.7, which comes out to approximately 0.497, which is 49.7%. So 49.7% of computers will last more than 7 years. This is very good news for somebody who wants a computer that lasts a long time. On the average, how long would 5 computers last if they are used one after another? Okay, well, let's think about this. So one computer part lasts 10 years on average. And if you're using them one after another, so if your first one lasts from 0 to 10 years, then your second one will take you to 20 years, your third one to 30, and then all the way up to 50. So we would expect this to be about 50 years if they're used one after another. Now, that's just an average, but we can't do better than that. We can just say, well, if the average is 10 years, then if I use one until it's broken, and then I use the next one, and the next one, and the next one, and the next one, I should be able to get by with 50 years worth. Okay, 80% of computer parts last at most how long? 80% of computer parts last at most how long? Okay, so here's our distribution. So along my time, I want to know 80% of computer parts last at most how long? Okay, well 80% of computer parts are going to be somewhere between here and some time t. So I know that the area from time 0 to time t under this curve, which is given by 0.1 e to the negative 0.1x, that area is going to be, I want it to be 80%. I need to find that value of t, and this guy comes out to negative e to the negative 0.1 t plus e to the negative 0.1 times 0, which equals 0.8. This is going to equal 1. This is 1 right here. If I subtract that over, I'll get negative 0.2 on the right. There's a negative on the left and a negative coefficient on the right, so this will be e to the negative 0.1 t equals 0.2. And if I take the natural log of both sides, I'll get negative 0.1 t equals the natural log of 0.2, and t equals the natural log of 0.2 divided by negative 0.1. So natural log of 0.2 divided by negative 0.1 gives me a time of about 16.1 years. So if you look at 80% of all computer parts, you'd say, well, 80% of computer parts last somewhere between 0 and 16.1 years. Again, a lot of those are going to be closer to maybe this has a 10% per year decay rate. So about 10% die per year if you think about it. And so a lot of them will die within the first few years, but also we see that there's a pretty high shelf life on some of them. Okay, what's the probability that it lasts between 9 and 11 years? Well, so that would be, you know, somewhere between, say, here and here. And so our setup is going to be very similar, except from 9 to 11, 0.1 e to the negative 0.1x. And so this comes out to, let me see if I can skip a couple of steps here. This will be negative e to the negative 0.1 times 11 plus e to the negative 0.1 times 9. And that looks a lot like what we've been doing, just in a short number of steps. So we'll get negative e to the negative 1.1 plus e to the negative 0.9, and we get about 0.074, which is 7.4%. So yeah, about roughly 7 in 10 computers will last between 9 and 11 years. That's not a huge outcome. Again, a lot of them last just a very few number of years, 4 or 5 years if you think about it, how long technology lasts these days, and very few will last a long time. So even though the average is 10 years, that's probably only because of the pull of outliers, like we saw back here with the mean and the median. The mean is going to be higher. 50% of 50% of customers, were there for under 2.77 minutes. So 50% of all laptop parts will probably die sooner than 10 years. But because of some extreme cases where certain laptop or computer parts last a long time, it could pull that mean up and make it look like it's larger. If I told you, on average, people spent 4 minutes at the post office, you might say, oh goodness, well, I'm probably going to have to be waiting for a while. But if I told you then that it's from an exponential distribution, you would recognize that although the mean is big, it's only big because of those extreme outliers, and a median might be a better measure of centrality.